Hello, so we are continuing our lesson on structure and bonding. And let's just take a quick recap of where we were on the last lesson. We were looking at these pictures here. Now, don't worry too much if I'm not going to ask you to draw one of these pictures necessarily or even draw one of these sort of diagrams at the top. I'm just trying to help you understand that there is this property called hybridization, which is the human way of trying to make sense of why compounds like methane have four equivalent bonds. Methane is totally symmetric. All the four bonds from carbon to hydrogen appear to be exactly the same. The issue was that the original form of carbon, when you draw its orbital diagram, doesn't seem to support that finding. It seems to say that you would only be able to make two bonds rather than four bonds because there's only two partially filled atomic orbitals. So then the chemist thought, let's do an excitation. This is more of a mind trick rather than a chemical reaction. It's just sort of a thought experiment. And said, well, let's just say one of these electrons went up a level. That would free up and actually create possibility for four bonds to be formed, because now that would make four sort of partially filled orbitals, which could create covalent bonds. But even that wasn't enough, because this would suggest that we would have three bonds of a certain flavor and then one bond made through the 2s orbital that was sort of a different flavor. So if this were true, we would expect there to be three bonds of methane that were similar and then one bond that was kind of an outlier. But we know that's not true. All the bonds are the same in methane. So then the idea was, what if these orbitals sort of hybridized into a new orbital called the sp3 orbital, and that all of those orbitals were at the same energy level? Then we could finally have four equivalent bonds. So you can see this is a lot of BS, basically. It's a lot of hand-waving explanations that we have to do to try and make sense of the reality of methane. It doesn't seem like a graceful or beautiful or even elegant solution by any means. It's simply just trying to force a square peg into a round hole. But it really, really makes our understanding of organic chemistry easier to understand. And so we're going to go ahead and go with it. Okay? And so we saw that methane, the carbon in methane, is sp3 hybridized. And then we went forward and we did the same thing with ethylene, which is this compound here. And we saw that the carbon in ethylene is sp2 hybridized. We saw that because in order to connect to three different atoms, only three of the orbitals were hybridized, rather than the previous example where we needed to connect four atoms. That's why we hybridized four. And you can see here, this carbon here, look how many different atoms it's connected to. It's only connected to 1, 2, 3 different atoms, and that's why we only hybridized 3 of them. So now let's take a look at one more example, just to try and drive this point home. Let's take a look at an interesting compound, acetylene. So we'll say example, carbon in acetylene. So acetylene has the following structure. There's a triple bond in there, and so we were interested in seeing what the bonding is for this carbon here. And so what you can see is that this carbon is only attached to two other atoms, hydrogen on the left and carbon on the right. And yes, it's a triple bond to the carbon on the right, but let's just say for now that it's attached to two different atoms, hydrogen and carbon. Let's see what the hybridization picture would look like in this case. So again, I will draw my little energy line going up. I'll have my 1s, my 2s, my 2p. I'll draw those atomic orbital lines, right energies, and now we'll fill in for carbon. Remember that carbon has the following electron configuration: 1s2, 2s2, 2p2. All right, we'll do an excitation again, just like before, just trying to be consistent with what we'd seen on the previous two slides. So if we do that, 1s, 2s, 2p, we'll get the 1s kind of staying out of this, and then we will get our 4 partially filled orbitals. Now let's do our hybridization. Okay, and now this time, instead of hybridizing 4, instead of hybridizing 3, let's just hybridize 2 and see what happens. So we're just going to grab these two bad boys and hybridize them together. Okay, and so we get 1s, we'll get sp, since we're just mixing one s and one p, and then we do still have some 2p orbitals left over. So we'll have our 1s orbital stay the same. We have 2 new sp hybrid orbitals, and we have 2 left over 2p orbitals. We can draw in our arrows here. So 1s orbital is like, what the heck's going on above me? I wasn't involved with this hybridization. The sp hybrid orbitals, those are partially filled, and the 2p hybrid orbitals, those are also partially filled. So this is what the atomic orbitals of carbon and acetylene would look like. And so now let's see what this bonding looks like. Let's see what this looks like when it's all connected. So we have carbon and carbon. And then connecting the 2 carbons, we have an sp orbital. And there's our sp orbitals on each carbon. And then connecting the carbon to the hydrogens on the right and left. Well, we're just going to focus on the carbon on the left. The hydrogens, of course, that just has a 1s orbital, so it's just sort of a sphere around it. Okay, and there's another sp orbital coming out towards that hydrogen. And then this carbon also has an sp orbital coming out towards that hydrogen. I really should show this overlapping more, so I'll just kind of draw that hydrogen overlapping. Okay, so we have a lot of sigma bonds here. Remember, a sigma bond is when we have the orbitals pointing directly at each other and the overlap is direct. Now, on each carbon we have 2 p orbitals. We have, and remember the p orbitals look just like perfect symmetric figure 8 kind of things. So we have 1 p orbital that looks like this. Maybe this is the pz orbital, for example. Remember there's 3 p orbitals. There's a pz, py, and a px. Maybe that's the pz. We don't really know. It doesn't really matter. And there's a second p orbital that's going to be at a 90-degree angle to that. Maybe that's the py orbital. So I'll kind of imagine that this orbital is kind of coming in and out of the page, kind of coming out of the page as kind of a perspective. Here we go. And remember, these p orbitals have phase, so let's kind of shade these in to show like this will be the negative side of the p orbitals. And then this will be the negative side of our other p orbitals. Okay, and this is what the bonding in acetylene looks like. We have actually 2 pi bonds. So remember, a pi bond is when you have this lined up orbitals, but the bonding is happening with electron density away from the bond axis. So it's not a direct overlap, but more of a side-to-side overlap. So we've created a pi bond there, but we've also created 90 degrees to that, a second pi bond. So the acetylene molecule has a pi bond going up and down. It also has a pi bond going sort of forward and backward. So 2 pi bonds in acetylene. And then in the middle, connecting the 2 carbons together, we have a sigma bond. So when you look at this triple bond, it's actually 2 different types of bonds. One of these bonds between the carbon and carbon is a sigma bond. That is this bond right here. But the other 2 bonds are pi bonds. Those are this guy here and this guy here. So, but we don't make that we don't distinguish that feature when we draw acetylene. We just draw a triple bond. But really what you have to understand is that one of these lines is sigma and the other 2 are pi. And so that's what the bonding looks like in acetylene. And so if we were to ask the question, what is the hybridization of this carbon, you would say that carbon is sp hybridized. That carbon is sp hybridized. And if you look at this page, what's the hybridization of this carbon? It's sp2 hybridized. So let me show you a quick trick. If you don't feel like drawing all these pictures and figuring this out, there is an amazingly fast shortcut to figure out what is the hybridization of an atom. And if you can count to 4, you can figure it out. Okay, so let's just go on to the next page and kind of summarize what we are talking about here. So this will be a summary of hybridization. And you're going to be like, oh, Dr. T, why didn't you just say this first? And we wouldn't have had to spend all that time showing those pictures. And while we're here, we'll also talk about geometry. Because the hybridization tells us information about the shape of the molecule. And the shapes of molecules are very important in organic chemistry. Think about those neurotransmitters that we looked at the beginning of this class. Those are those molecules that your brain uses as signaling chemicals to help conduct neural signals. Those molecules fit like a lock inside of a key in specialized receptors. So the shape of organic compounds is very, very, very important to us. We would not be here today. Our bodies would not function if it were not for the specific shapes of the compounds, organic compounds in our bodies. Okay, so let's make a little bit of a table here. And I'm going to create a first column, and we'll name that steric number. I'll define what that is in a moment. So we'll just call that steric number. And then I'm going to have a second column called geometry. And geometry means shape. And I'm going to be a little bit more specific. I'm going to call this the electronic geometry. Because remember, all those things we were looking at on the previous page, those were all electrons inside of those orbitals. So it's really the electrons that are giving the shape to molecules. So it makes sense to call this electronic geometry. We'll also be able to talk about the bond angles. And finally, we can talk about the hybridization. Awesome. Okay. And I'll just underline for consistency. All right. So if the steric number is 4, the electronic geometry is said to be tetrahedral. And it's okay, I know I haven't defined what steric number means yet, but I will in just a moment. And the bond angle is 109.5 degrees. And the hybridization is sp3. If the steric number is 3, the electronic geometry is said to be trigonal planar. The bond angle is 120 degrees. And the hybridization is said to be sp2. And if the steric number is 2, the electronic geometry is said to be linear. The bond angle, 180 degrees. And the hybridization is sp. Okay, so now let's define what is steric number. So steric number is equal to the number of sigma bonds plus lone pairs. Lone pairs. The number of sigma bonds plus lone pairs. So let's do an example here of CH3, methane. So I would have to specify, tell me the steric number of a particular atom, and let's say, what about the carbon in methane? So we're looking at this carbon. How many sigma bonds does it have? 1, 2, 3, 4 sigma bonds. And how many lone pairs does it have? Those are the little dots. None. So the steric number is going to be steric number equals 4 plus 0, which equals 4. So the steric number is equal to 4, which means that the electronic geometry or shape of our methane molecule is tetrahedral. The bond angle, which is the angle between these hydrogens, is 109.5 degrees. And we know that the carbon is sp3 hybridized. So really, we get a lot of information just by counting the number of bonds and lone pairs. Let's do a couple more examples and define a few more terms. So electronic geometry. Well, the electronic geometry, that's the shape of the molecule. And because we call it the electronic geometry, that shape is going to include the lone pairs. That's really just a technicality. If I just said the geometry of the molecule, it would sort of imply that we're not going to count the lone pairs. But if we say electronic geometry, it's going to include the lone pairs in that shape. Let's do an example of ammonia. So ammonia looks like this. NH3. So let's take a look at, let's say I asked you, what is the electronic geometry of nitrogen? Well, the first thing we would have to do is count the steric number. How many sigma bonds do we have? We have 1 sigma bond, 2 sigma bonds, 3 sigma bonds, and 1 lone pair. So the steric number is going to equal 3 sigma bonds plus 1 lone pair. Be careful, it's lone pair, not electrons. So pair meaning 2 electrons. So 3 plus 1 equals 4. So the steric number is 4. So that means that NH3 nitrogen is tetrahedral. And what's the hybridization? sp3 also. And so that's actually an important note, is that other atoms besides carbon can be hybridized. In fact, any atom with s and p orbitals is going to be hybridized in organic chemistry. So we can just mention that here. So any element with s and p orbitals can hybridize, will hybridize. So that means you can talk about what is the hybridization of carbon, nitrogen, oxygen, even chlorine. We can talk about the hybridization of all of these atoms, but not hydrogen. Hydrogen is an atom that very commonly appears in organic compounds, but it only has s orbitals, so it cannot hybridize. You can't have like an sp3 hybridized hydrogen. You need at least one p orbital to be able to do that. So hydrogen would not be able to hybridize. And one last thing I want to mention here is, let's take a look at this compound here. We've seen this one before, ethylene. Let's say I asked you to count the steric number of this carbon here. We would count the number of sigma bonds. And so this can be a little bit tricky. Like, are both of these sigma bonds? Are both of those pi bonds? Is one pi and one sigma? I want you to recognize that for double and triple bonds, those only count once. Remember that a double bond is comprised of a sigma bond and a pi bond. And a triple bond is composed of a sigma bond and 2 pi bonds. So that means do not count double bonds twice for steric number. They only count as 1. And same with triple bonds. They only count as 1 as well, because triple bonds only have 1 sigma bond still. We saw that on the previous page here, where even though this is a triple bond, it's actually only 1 sigma bond and there's 2 pi's there to make it triple. Okay, so we're going to count the steric number of this carbon here. So steric number equals the number of sigma bonds. In this case, there's 1 sigma bond, 2 sigma bonds, 3 sigma bonds only, not 4, plus the number of lone pairs. How many lone pairs are on that carbon? 0. So 3 plus 0 equals 3. So that means that this carbon has a steric number of 3. The electronic geometry is trigonal planar, the bond angle is 120 degrees, and the hybridization is sp2. And one last thing I'll mention, I lied. I said there was going to be one last thing, but I do want to mention one thing here, is bond strength. And I know this is kind of out of place, but just that a triple bond, just like you would expect, is stronger than a double bond, which is stronger than a single bond. So just be aware of that. Bond strength trends. Triple is more strong than double, which is more strong than single, just like you would expect. Okay, so now this is amazing because I can give you any molecule and you can tell me the hybridization of any atom I specify without having to draw all of these complicated pictures. You just literally count 1, 2, 3, 4, and you're going to find the steric number. Now, keep in mind the steric number in this class is only ever going to be 2, 3, and 4. So if you count a steric number that's 5 or you count a steric number that's 1, you know you're doing something wrong. It's always got to be one of these options, and the hybridization is always going to be one of these options. And now you have a super cool shortcut to determine that without having to draw a complicated picture. All right. Sort of the last topic before we change gears a bit and talk about drawing molecules a little bit, and that is the concept that you've probably heard of before called electronegativity. And so I'm just going to kind of draw a simplified periodic table. So boron, then comes carbon, then comes nitrogen, then comes oxygen, then comes fluorine, then comes chlorine, bromine, and iodine. And each of these atoms has an electronegativity value that you should kind of know the general ranges of these electronegativities. Boron is 2.0, carbon is roughly 2.5, nitrogen is 3.0, oxygen is 3.4, fluorine is 4.0, chlorine is 3.2, bromine is 3.0, and iodine is 2.7. So this electronegativity comes into play later in the class, but I just want to introduce this topic now when we're talking about bonding. You'll see that the reactivity of organic molecules a lot of times has to do with electronegativity. So just keep this thought in mind, and remember that this is a periodic trend, meaning that as you go right along the periodic table, and as you go up on the periodic table, the electronegativity values kind of trend up towards that direction. So just keep that in mind. So I'll just say periodic trend. So again, I'm never going to ask you on a test, what's the electronegativity of fluorine, and ask you to come up with 4.0, but I might say, who is more electronegative, fluorine or oxygen? And you would say fluorine is more electronegative. Okay, so now that we get to talk about something fun, which is drawing the organic molecules, and then we're almost done with this lesson. So this is perhaps the most important slide in this entire class, because being able to draw and interpret these bond line drawings is going to be critical moving forward. Bond line drawings. And so the take-home message here is that there are multiple ways that we can draw organic compounds, but bond line drawings are by far the best. We've already seen Lewis structures being used to represent organic compounds. And what you'll notice about Lewis structures is look at how long it takes me to draw a Lewis structure. If we had to draw a Lewis structure every single time we wanted to draw an organic molecule, this class would take a lot more than 8 weeks. So this is the Lewis structure. So chemists are like, we need a better way to represent these sort of molecules. So they came up with something else called the condensed structure. The condensed structure kind of came about around the same time the typewriter was used, because it is really convenient for typing out formulas on the computer. So this is actually the representation of the exact same molecule in a condensed structure form. Notice how it all fits on a single line. The double bond is sort of represented by an equal sign, and you just sort of slam all the atoms together, CHCOCH3, just to kind of show how things are connected in order. But we lose a lot of the information. Like, for example, we don't see the CO double bond. That sort of must be implied somehow. And we don't see the lone pairs on the oxygen, so there's a lot of information that's sort of lost with the condensed structure. Okay, so the bond line drawing kind of gets the best of both worlds. It's really fast to draw, and it still preserves a lot of information from the Lewis structure. And let me show you what the bond line structure of this compound would look like, and time me, see how long it takes me to draw this. Done. That is the bond line structure for this molecule. For the bond line structures, you can include lone pairs on things like the oxygen and still preserve that information, but a lot of times the lone pairs are just sort of dropped off. So if you don't see lone pairs, that's just chemists being lazy. You don't have to include lone pairs unless I specify. Okay, so let's try and understand what's going on with these bond line structures. It seems like a lot of atoms seem to have been truncated, meaning they've been left out. For example, we don't see any of the carbons and hydrogens at all. We do still see like this double bond here, but it seems like a lot of atoms are left out, and indeed that is the case. So let's take a look at an example of a bond line structure and see what's going on here. So this would be a bond line structure of a compound, and let's count how many carbons it has. So it turns out in the bond line structure, every sort of angle change represents a carbon. So like every end of every line and every angle change in every line represents a carbon. So this is a carbon, 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 this is a carbon in our little structure here. So let's count up the carbons. 1, 2, 3, 4, 5, 6, 7 carbons. Okay, what about the hydrogens? You'll notice that in our bond line structure here, all the hydrogens got eliminated as well. And that is because the hydrogens are so common in organic chemistry that it just gets really tiring to draw them all. So instead, in the bond line drawing, we assume that any areas left blank, like that is nothing is drawn there, is occupied by invisible hydrogens, which are sometimes called implicit hydrogens. So for example, let's take a look at this carbon here. This carbon here is making two bonds, one bond to the right to a carbon and another bond to the left to another carbon. That means that this carbon, as drawn, is only making two bonds. But how many bonds does this carbon want to make? 4. All carbons want to make 4 bonds. So that means there are 2 hydrogens hiding here that aren't drawn in to make up the 4 total. So let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. And now we can kind of draw out this into a Lewis structure form just to see what it looks like. So we have carbons in a hexagon. Then we have another carbon coming out of the hexagon. And now we just need to add hydrogens so that each carbon makes 4 bonds. So add hydrogens as needed so that each carbon makes 4 bonds. So we'll add 2 hydrogens here, 2 hydrogens here, 2 hydrogens here. Two hydrogens here. This carbon here only needs 1 hydrogen because it's already making 3 bonds. And then this carbon up here needs 3 hydrogens because it's only making 1 bond. So wow. You can see that it's much faster and easier to draw a bond line structure than a Lewis structure because you don't have to draw all the carbons out and you don't have to draw all the hydrogens out. Let's take a look at one more example. All right, how many carbons does this compound have? Again, we'll just count sort of the ends of the lines and the angle changes along the bending line. So 1, 2, 3, 4, 5, 6. This compound has 6 carbons. And see for practice if you can count how many hydrogens that compound has. See if you can count how many hydrogens that compound has for extra practice. What about double and triple bonds? Double and triple bonds. Those are very common in organic chemistry, and so we can represent double and triple bonds that look like this. Again, we don't draw in any of the carbons or the hydrogens, but we do include the double bond there. And so this compound would have how many carbons? Let's count. 1, 2, 3, 4, 5, 6, 7 carbons. And we could also do a triple bond. Remember that triple bonds, the carbons involved with the triple bonds are sp hybridized, which means that they are linear. So notice that when we draw our bond line drawing, we have it kind of straight line through that triple bond, showing that 180-degree bond angle. How many carbons does this compound have? 1. This is a little tricky, so be careful when you count. 1, 2, 3, 4, 5, 6. So this compound has 6 carbons. Can you see that? So the ends of the triple bond each have a carbon there. 1, 2, 3, 4, 5, 6. And again, for practice, why don't you try and draw in all the hydrogens and try and count how many hydrogens this compound would have. Now, so far we've just looked at bond line diagrams for the previous examples with compounds that only contain carbon and hydrogen. But as we know, organic compounds can contain other atoms besides carbon and hydrogen. They can have oxygen, they can have nitrogen, they can have chlorine. How are those dealt with? And so those types of atoms actually have a name. They're called heteroatoms. Heteroatoms are any atom other than carbon or hydrogen. And so we call those heteroatoms. So let's take a look at a Lewis structure type drawing first. So okay, there's a Lewis structure. It took me forever to draw it. How can we replace this into bond line form? Well, just take a look at what we have here. We have carbon and carbon connected to each other. So that'll just be a line. Remember that this is a carbon and this is a carbon. And then connected to one of those carbons, we have an oxygen. So we'll draw another line down and then put an oxygen there. And then connected to that oxygen, we have a hydrogen. So we just write an H there. Notice that we must draw all hydrogens attached to heteroatoms. So that would be how you can redraw that molecule as a bond line drawing. Notice a couple of features here. The carbons and the hydrogens are completely left out and they're just turned into lines. The oxygen is replacing at the end of the chain a carbon. So keep in mind that this right here is not counting as a carbon because oxygen is capping it off. So this compound only has 2 carbons, 1, 2. A lot of students maybe sometimes get confused and think this is a third carbon, but that is not the case. The carbon that would be there has been replaced by oxygen. And also notice you do not have to draw the bond between the oxygen and the hydrogen. You can just write OH. And the implication is that they are bonded together. Also notice that the lone pairs were not drawn in, and that's totally acceptable. You can leave out lone pairs in bond line drawings. Okay, one final thing I want to say about bond line drawings, and there's a lot of bond line drawing practice on problem set 1. So if you want to just stop right now and do some practice, why not download problem set 1 and check out that first page. There's some amazing bond line drawing practice. You are going to be amazed. This is kind of like a second language. At first it'll be a little uncomfortable, but soon it'll just feel so natural. It's a really natural way to represent organic compounds, and I want you to get good at it right away. So check out problem set 1. Okay, one last thing I want to talk about is dealing with formal charge. And what we'll find is in this class, there'll be some times where we have carbon with a formal charge of either -1 or +1. So just for simplicity's sake, let me go ahead and draw a compound that has both a minus and a plus charge carbon in it. So over here on the left, I'll create a negatively charged carbon with a lone pair on it. And over here on the right, I'll put a positive carbon, okay? So now let's draw the bond line, let's take our bond line structure that we have here and turn it into a Lewis structure. So this is similar to what we drew before. Let me just draw in the carbons, and what we're gonna talk about is the hydrogens really is interesting for us. Okay, so there's the carbons in the ring, and then we have another carbon outside the ring. And so the thing to keep in mind is remember when we were drawing the Lewis structures, we needed to add hydrogens such that each carbon had 4 bonds. So for example, we added 2 hydrogens to this top carbon here so that it would create 4 bonds. For carbons that have a negative or positive charge, they only make 3 bonds. So for example, this carbon here, which we saw had a lone pair and a negative charge, we only want to add hydrogens such that it makes 3 bonds, not 4. So right now this carbon is making 2 bonds, so we'll only need to add 1 hydrogen there. This carbon is neutral, so it needs to make 4 bonds. This carbon is neutral, so it needs to make 4 bonds. This carbon is neutral, so it needs to make 4 bonds. This carbon is neutral, so it needs to make 4 bonds. And this carbon up in the upper right has a positive charge, So it only wants to make 3 bonds, just like the negative carbon. And so instead of adding 3 hydrogens to that carbon, we'll just add 2. And now that carbon is making 3 bonds. So take-home message, if you end up with a carbon that has a negative or positive charge, make sure that it only has 3 bonds being formed rather than the usual 4. You may be wondering, why is this? We can look at the formal charge formula to remind ourselves why this is the case. So remember, formal charge equals number of valence electrons minus the number of bonds minus the number of lone pairs or unshared electrons. So bonds minus unshared electrons. I'll just say UEs. So let's take a look. So if we have a carbon with a -1 charge, so that means the formal charge will be -1, equals the number of valence electrons. How many valence electrons does carbon have? If you remember, it has 4. Minus the number of bonds. Let's just set that equal to X for now. We're going to solve for X and see how many bonds that carbon is supposed to make. Minus the number of unshared electrons. We'll take a look at this. It's a negative charge and it's got 2 unshared electrons, so -2. Okay, now if we go ahead and, do this math here, we'll find that we do. So -1 equals 4 minus 2 is 2 minus X. Subtract 2 from both sides, you'll get -3 equals -X. And so therefore, X equals 3, meaning that we would expect that that carbon would make 3 bonds, and indeed it does. And we can do the similar thing for the positively charged carbon. If the positively charged carbon has a formal charge of +1 equals 4 valence electrons for carbon, minus the number of bonds, we'll set that equal to X, minus the number of unshared electrons. In this case, there are 0 unshared electrons on our positively charged carbon. So that's going to be 1 equals 4 minus X. Subtract 4 to both sides, so get -3 equals -X. So then again, 3 equals X. So that's why you can see that whether you have a carbon with a negative charge or a positive charge, that carbon is going to be making 3 bonds rather than the usual 4. All right, so I think actually I want to stop right there. This would be a great opportunity to boot up that problem set 1 and check out the first page of that problem set, because this is going to be amazing practice for what we've just talked about today.